Have you ever just stared at a function, something like sine of x squared, and thought, now what? Well, if you have, you're in exactly the right place. Today, we're going to unlock one of the most powerful tools in all of calculus, the chain rule. And I promise you, by the end of all this, you'll see it's way less about scary formulas and a lot more about something as simple as Russian nesting dolls. Let's dive in. So here's the core puzzle. You're probably comfortable finding the derivative of sine of x. No problem. And you definitely know the power rule for x squared. But what happens when you mash them together? How do you handle a function that's literally tucked inside another one, like sine of x squared? This is the exact problem the chain rule was born to solve. And here's our game plan for cracking this thing. First up, we'll break down this puzzle of functions inside functions. Then we'll use a super simple analogy, nesting dolls, to make it all just click. After that, we'll introduce the tool itself, the chain rule, and then, you know it, we're going to use it to solve that problem from the first slide. And finally, we'll see how this one idea just blows the doors open for even more advanced stuff in calculus. All right, so let's dig in. What really makes sine of x squared so tricky? Well, it's not just two functions hanging out together. It's a very specific kind of structure, a composite function. That's the formal name for it, a composite function. And look, that's just a fancy way of saying we have one function living inside of another. You can almost think of it like an assembly line, right? You start with x, the inner function g does something to it, and then that entire result gets passed along to the outer function f. So for our problem, sine of x squared, the outer function is the sine part. It's the big shell. The inner function is what the sine is acting on, in this case the x squared. Just being able to see those two distinct parts, the outer and the inner, that is the absolute key to getting this right every time. Okay, to really make this idea stick, let's just forget about math for a second. Let's talk about something way more intuitive, Russian nesting dolls. Seriously, just picture a composite function as a matryoshka doll. You've got that big outer doll, and if you want to see what's going on inside, you have to deal with that outer layer first. There's no way to just magically get to the tiniest doll in the center. You have to work your way in, one layer at a time. And this maps perfectly to our math. The big outer doll, that's our sine function. The smaller inner doll, that's the x squared. And the real question we're asking with calculus is this. How does the entire set of dolls change when that tiny little doll on the inside changes just a little bit? So now that we have this fantastic nesting doll idea locked in our brains, we are totally ready for the tool. We're ready for the rule that lets us systematically unpack these functions. Okay, here it is, the formal definition of the chain rule. I know, it sounds a little wordy, maybe a bit academic, but the idea behind all these words is actually incredibly simple. And here's what it boils down to. This is all you really need to remember. It's the derivative of the outside times the derivative of the inside. That's it. You take the derivative of the big nesting doll, leaving the little one inside for a second. Then you multiply all that by the derivative of the little nesting doll itself. That's the whole trick. Now, you'll often see it written like this, using what's called Leibniz notation. It might look a little intense, but all u is a temporary nickname for our inner function. What's so cool about writing it this way is that you can almost see how the du parts cancel out, leaving you with dy by dx. It literally shows you the chain of rates that connects the outside to the inside. Pretty neat, right? All right, enough theory. We've got the concept, we've got the analogy, we've got the rule. It is time to go back to that very first question and just solve it, step by step. Let's just walk through the process. Okay, step 1, what's our outer doll? It's sin something, or sin u. Step 2. What's the derivative of sin u? Well, that's just cos u. Easy enough. Step 3, what's our inner doll? It's x squared. Step 4, what's its derivative? 2x. And now for the grand finale, step 5. We multiply them together, and we just have to remember to put the original inner function back where that u was. And this table just lays it all out perfectly. We take the derivative of the outer part, sine, which becomes cosine, but we keep the original guts inside it, so cos of x squared. Then we find the derivative of the inner part, x squared, which is 2x. And finally, we just multiply those two pieces together. And there we have it. The puzzle is solved. The derivative of sine of x squared is 2x times cosine of x squared. Something that seemed kind of impossible at the start is now just a straightforward, repeatable process. That's the power of the chain rule. But hang on. The chain rule is not just a one-trick pony. Its real power is that it's the foundation for solving even bigger, more complex problems in calculus. So up until now, you've probably been dealing with what we call explicit functions, where y is all nice and tidy on one side of the equation. But a lot of the time, variables are all mixed up together in what we call an implicit function. Think about the equation of a circle. X squared plus y squared equals 1. How on earth do you find the derivative of that? You guessed it, the key is the chain rule. We do something really clever. We just pretend that y is some secret inner function of x. It becomes our new nesting doll. So every time we take the derivative of a term that has a y in it, we have to apply the chain rule. It's the bridge that lets us solve these otherwise messy problems. So think about it. We started with a simple puzzle, sine of x squared, and we ended up with a key that unlocks some of the biggest ideas in calculus. The chain rule isn't just another formula to memorize. It's a way of seeing relationships, seeing how a change in one tiny part can create a chain reaction through an entire system. Which kind of leaves us with a final thought. Now that you have this tool for connecting the rates of change between linked things, what other real-world chains can you start to see? You know, things like the expanding ripples in a pond or the inflation of a balloon. What can you now understand through the amazing lens of calculus?